All right, so we're still talking about the chain rule. I'm going to do a couple of examples here. So I'll start by just reminding us of what the chain rule is. The basic idea is it tells us how to take derivatives when we have a composition of functions, right? So if I've got f composed with g and I take the derivative of that with respect to x, I get the derivative of f, except we're taking it with respect to g of x. So we look at the derivative of f, but instead of x's, we put in whatever g is. And then we'll see g prime of x, right? So a lot of the, one way people often say it is we take the derivative of the outside function in terms of the inside, and then we take the derivative of the inside function, okay? So this is what our chain rule derivatives will look like. So let's start with a derivative of a cosine function. Get an example of a trig function happening here. So I want to do the following: the derivative of cosine squared. Let's make it theta. Let's do some other variables. So dd theta cosine squared of theta. And let's use this as an opportunity to make some notes about some notation with trig functions in case it's been a while. So cosine squared theta, remember, means cosine of theta squared. In other words, it's cosine of theta times cosine of theta, right? This is, of course, different than cosine of theta squared, which is like cosine of theta times theta, right? The squaring is happening inside the thing you're putting into it. A confusing spot for trig functions is we use an exponent, the exponent -1 here, and we don't use it the same way as the 2, right? This is a kind of a unfortunate situation we find ourselves in. But everybody does it, and you'll get used to it if you haven't already. This does not mean cosine of theta to the -1 like this, right? This would, of course, be 1 over cosine of theta or secant of theta. So we already have a name for that. Cosine with this little -1 is the inverse cosine or the arc cosine of theta, right? So it's just one of those things we have to remember. Okay, just saw an opportunity to mention that, but let's get back to the chain rule. So seeing this cosine squared theta this way makes it a little bit easier to see that this is a chain rule. So let's go ahead and write it this way. We've got, oops, cosine of theta squared. So here we've got, I like to do some work off to the side. I want to write my function. If I think I have a chain rule opportunity, then I should be able to write the thing I'm taking the derivative of as a composition of 2 or more functions. So let's see if that's true. If I take the function f of x, let's do theta. F of theta is equal to theta squared, and g of theta is equal to cosine of theta, then it is certainly the case that f of g of theta is equal to the cosine of theta, this whole thing squared. All right, so in terms of our newly defined functions, we're looking for a derivative of a composition of functions, and we simply apply the chain rule. So we'll have f prime g of theta times g prime of theta. So then I just need my derivatives, right? So f prime of theta is 2 theta. And I like to write f prime of g of theta to be very clear, right? If f prime is 2 theta and I put in g of theta instead of 2 theta, I get 2 times whatever g of theta is. And g of theta happens to be cosine of theta. And then g prime of theta is the derivative of cosine, which we know to be negative sine theta. So now I have all my pieces. I just need to write them in. F prime, this first piece, f prime of g of theta is 2 cosine theta. And then I'm multiplying it by g prime of theta, which is negative sine theta. I'm going to just rearrange it to make it look a little cleaner. 2 cosine theta, sine theta. And there is our derivative of cosine squared theta. -2 cosine theta, sine theta. Right, this is another example where there's a different way to do this one. We did it with the chain rule. I could just as easily right, cosine squared theta is cosine of theta squared, so we're multiplying it by itself. So I could have written this way. And then we're doing a product rule. It doesn't matter that they're both the same functions. There's still 2 functions being multiplied by each other. And we take that derivative by taking the derivative of the first, negative sine theta, times the second function, leaving it alone. And then I'll take the derivative of the second function, which is the same thing, and multiply it by the first function. Well, those are just the same thing. We've got a negative sine theta and a cosine times cosine theta, and we've got 2 of them. So we have -2 sine theta, cosine theta, right? So again, as in the previous videos, if there's multiple ways to do it, as long as it's true that we have a product function, and here we do, this is my f times g, there's nothing that says they can't be the same function. They are 2 functions that we're multiplying by each other, so we can apply the product rule and we get a correct result. We also can think of this as a composition of functions. That's also true, so we're free to use the chain rule. And so both of these are correct, and of course they get the same answer. You will find sometimes, if you're experimenting with this, want to see how it works on some other examples, you might find somewhere, depending on how you do it, your answer looks a little different. But if you've done it correctly, then there's often some algebraic, then there should be some algebraic manipulation or some reason that the different expressions are equivalent. For instance, in trig functions, you might use some trig identities together. We didn't need to here, but there are some out there where, or I guess even as I've written these here, there's a simple algebraic switch, and sine theta, cosine theta is the same as cosine theta times sine theta. All right, let's do another example. Here we're going to be combining the chain rule with some other rules. I've got the function y equals x to the 5th minus 1 to the 7th times x cubed plus x cubed. So one strategy that we're not going to do is we could expand this whole thing, right? So if I expand this whole thing, I'm going to get a massive polynomial, right? It looks like we'll have x to the like 44th power and then a whole bunch of other terms, right? But that, of course, would be an obscene amount of work, okay? So we're going to use the methods we now have. I'm going to think of this in a couple different steps. The first step is to notice I can think of this as a function and this as a function. So I have a product rule. So y prime is going to be the derivative of x to the 5th minus 1 to the 7th. That's my first function, the derivative of the first function, times x cubed plus x, the whole thing cubed. Then I'll take the derivative of the second function and multiply it times the first function without doing anything to that one, right? Okay, so there's my first step. This is a really good strategy to start using when we get complicated derivatives. Don't try to do everything at once, right? I don't know what these derivatives are, right? I've got 2 expressions and all they represent is the derivative of this thing, right? I've got this, the derivative of that first quantity and the derivative of the second quantity, but I don't know what those are yet, but that's fine because first I wanted to think about just the product rule. Now I'm going to think about those derivatives. I'm going to do that work over here. If I have d dx x to the 5th minus 1 to the 7th, this is going to be the derivative of f of g of x, or at least I'm hoping to. So let's see if we can get the right functions. If I have x to the 7th and g is x to the 5th minus 1, then you can see that if I take that this thing here is f composed with g, right? I'm taking x to the 5th minus 1 and putting it into x to the 7th. We get x prime of x is 7x to the 6th. So f prime of g of x is 7 times x to the 5th minus 1 to the 6th. And then g prime of x is 5x to the 4th. So now this chain rule, right? We wrote it as a composition. That means we can use the chain rule. We get f prime of g of x, which I have written right down here, 7x to the 5th minus 1 to the 6th power, times g prime of x, which I have right here, times 5x to the 4th. So now I can replace this expression, this abstract notion. Here goes, in this spot, we should write whatever the derivative turns out to be, and now I have it. And let's make it a little bit simpler. I can write this as, let's call it 35x to the 4th times x to the 5th minus 1 to the 6th. So I have 35 x to the 4th, x to the 5th minus 1 to the 6th times x cubed plus x cubed. All right, now we need this second derivative. d dx, x cubed plus x cubed. Very similar idea. I'll try to write this as a composition again. So this is what I'm hoping to do. I'm hoping to use my chain rule. F prime g of x, g prime of x. So what if I let f of x equal x cubed, g of x is equal to x cubed plus x. So if I put g into f, then that certainly is a composition that is equal to this original function. And then our derivatives are simple enough. We've got the power rule. If I take f prime of g of x, I've got 3x cubed plus x squared, and then g prime of x is 3x squared plus 1. And so now I've got 3x cubed plus x squared times 3x squared plus 1. Okay. So now I'm going to go back, put all of these things together. So I've got 3x cubed plus x squared times 3x squared plus 1. So there's the derivative, the thing underlined in red. And then I've still got this final x to the 5th minus 1 to the 7th. And there is a perfectly good expression for this derivative, right? There's no reason I need to expand all this, or at least we don't have one right now. There are things you might do in your career where expanding this might be useful, but there's no way I would ever expand it if I didn't have a good reason to, right? This would get very, very awful. And this is a perfectly reasonable way to write this function. We can easily evaluate it. We can know lots of things about it looking at it. So I'm just going to leave it as is. Okay, that is it for this example. Sorry, it's not it for everything. Let's do one more example expanding on this. Let's look at y equals sine of x. Well, let's write it in a more confusing way just to sort through it and then explain it. So this is going to be sine squared of x cubed. All right, I want to take the derivative of this function. So let's again deal with this exponent here. This thing could be written maybe more clearly as sine of x cubed, the whole thing squared. Okay. So I'm looking at this, and again, it looks like we've got a chain rule. I see some functions inside each other. So let's figure out what functions we can put inside of each other to get this, what composition we can write. So I'm going to start with f of x is equal to x squared, g of x is equal to sine of x cubed. So then f of g of x is going to be sine of x cubed squared, right? So taking the derivative of this function means taking the derivative of f of g of x, which is of course f prime g of x, g prime of x. So let's go ahead, take the derivatives that we need over here. So I have f prime of x is equal to 2x. And then I say g prime of x. And I notice now that g prime, I don't have a rule for. This isn't just the trig function. This is the trig function with a polynomial inside it. We have another composition here, right? So this function that I tried to write as the composition of two functions, I now see as the composition of three functions. I've got this nested doll situation happening on functions inside of functions inside of functions. That's fine. We can deal with this. What do we need? So in order to finish our derivative, right, I've got f prime of g of x. That's easy enough to write down. That's 2 times sine of x cubed. The last piece is I need g prime of x, right? But I can't use my simple derivative rules, but I can find g prime of x because I just said it's another chain rule. So let's find g prime of x over here. d dx of sine of x cubed. It's going to be d dx of, let's write the functions we need to make this a composition. Let's give it the names m of n of x. So m and n will be my new functions. So the derivative will be m prime of n of x, n prime of x, right? So what are my two functions? Well, it looks like I will need the outer function to be the sine of x, the inner function to be x cubed. And you see when you compose those, we get what's up there. So m prime of x is going to be cosine of x. M prime of n of x is going to be cosine of x cubed. And n prime of x is 3x squared. Okay. And so let's put everything in its place. M prime of n of x is cosine of x cubed. N prime of x is 3x squared. So the derivative of sine of x cubed is, I'm going to write this as 3x squared cosine of x cubed. Actually, no, I'm going to write it as written for now. Sorry, just realized I want to be a little clearer what we're doing next to see this. Okay, that is g prime of x, right? That's what g of x was sine of x cubed, and there's the derivative. So now I know this derivative is cosine of x cubed times 3x squared. So now I have everything I need to write this derivative. Y prime is going to be f prime of g of x. That's all the way over here. 2 sine of x cubed times g prime of x, which is cosine of x cubed, which is 3x squared. Okay. Now let's look closely at this function and our derivative, right? So let's look at the top. Sine, the quantity squared of sine of x cubed. What have we done? We've put x cubed inside of sine, and then we've put sine into the squaring function, right? So what do we have first? This is our derivative of the squaring function, right? We pull a 2 down. So that's like the derivative of the outside function, the squaring function, 2 down times x, but instead of x, it's whatever was inside. And so we have 2 times sine of x cubed. So we have the derivative of squared times the stuff inside. Then, so there's our first function is squaring, our outermost function is squaring. Then we have sine is our next function, right? And we have the derivative of sine, cosine, but not of sine of x, it's cosine of the thing that was inside sine, right? We leave that inner function alone, the x cubed. So we have the derivative of the squaring function of everything put inside the squaring function times the derivative of the sine function of everything that was inside the sine function. And then finally, we have the derivative of the thing that was inside sine, right? Symbolically, what we just did was see that the derivative of three nested functions was the derivative of the first one, leaving the inside stuff alone. Then we have the derivative of the next nested function, leaving the stuff inside alone. And then we have the derivative of the final function, right? I guess for our case, it was more like e dx of, I think we called it f, and then we had g of x, but then we split g of x into m of n of x. Is that enough? Seems like too many, but in any event, we ended up with f prime of m of n of x times m prime, f prime of m of n of x times m prime of n of x times n prime of x, right? And if you had 8 functions nested, you'd get the derivative of the outside function, leaving everything alone, times the derivative of the next one with everything inside it, of everything inside of it, and you just keep, right? It's this nested doll thing. You just keep the derivative of the outer thing and leaving the inside alone, then the derivative of the next inner thing, leaving everything else alone, and on down the road, right? So it's however many functions we end up with, we can use the chain rule over and over. You just have to organize, right? This took a lot of steps, but every step we did was just an application of the chain rule or one of our basic derivatives, our power rule or something like that, right? And we're going to see that with the basic rules that we've had, the power rule, constant multiple rule, adding and summing, product rule, quotient rule, and chain rule, we can take derivatives of a ton of the functions you're likely to see, right? We won't do this one right now, but if we take a function and we just start putting together different things, right? This is a really ugly derivative to take, right? But if we broke it down, we've got a quotient rule. We've got this thing on top of this thing. We do a quotient rule. To do the top quotient rule, to do the derivative of the top, we'd have a product rule. We have this function times this function. And then to take the derivative of this second function on top, we'd have a chain rule. We have all of this inside of sine. But then to take the derivative of everything inside, we have a quotient rule, right? Same thing on the bottom. We've got a chain rule with squared and cosine. We've got a quotient rule over here. Then we have to add or subtract them together, right? So there's a whole bunch of stuff to do. But if we do it a piece at a time, it's doable. It would just take a long time. So that's my plug for organizing, right? If you want to try this one, that's a great one to try. I'm not going to do it right now. That's it for this one. I will see you in the next one. Thanks, everybody.